So what I want to look at here is how to use all the stuff that we've been learning about the graph of sine and cosine in order to help us create a model. Now listen, I want you all to make sure that you're paying close attention to this, because if you miss one step, then you're going to be really lost as to how in the world we got that. Okay? There are a number of steps to this. And it doesn't matter a whole lot which order you do them in, but you are going to have to do all of them in order to get the complete model. And really this takes a lot of understanding about the graph of sine or cosine, whichever one you're using, in order to come up with the model given certain information. Okay? Now, I'm going to use the example here of the phases of the moon. This is kind of a neat one here. I have a calendar from last year in January, January 2016, of the different phases of the moon on each day of the month. And as you can see here, on the 10th, the moon was totally dark. We had a new moon. Okay? And then on the 24th, we had a full moon. Okay? We're actually going to use those 2 days to help us construct a model. We're going to assume that the phases of the moon go in a sine wave kind of pattern. We would need to verify this by looking at a lot of different points and seeing if it does repeat this way. But we're going to create a model using these 2 basic points. Okay? Now, before we can create a model, we need to define variables. And obviously, we can't have our variable equal nu or full or crescent or gibbous or something like that. All right, the different names for the phases of the moon. So what we're actually going to do is we're going to make our y equal the percent of the moon that is lit up. Okay? So we're going to call our new moon 0%. There's 0%. And we're going to call the full moon 100%. Okay? Now, in this particular case, it happens to be 0 and 100. But no matter what you're working with, you always want to identify what that lowest and highest point are. Okay? Because as we think about this in terms of our sine or cosine graph, and we're going to use sine for this one.
How do you know which one to choose?
What do you mean which one to choose?
How do you know if you're going to use...
Oh, sine or cosine?
Yeah.
In fact, it doesn't matter. Because remember, they're exactly the same shape, just one shifted over, pi over 2. So, if you use sine and I use cosine, they're going to be identical except for the horizontal shift. That'll be the only thing different. The period will stay the same, the amplitude's the same, the vertical shift will be the same. Okay? When I ask you to do this, I will tell you to use sine or to use cosine. Okay? And we do that just to kind of limit the variation and possibilities. There's already an infinite number of possibilities, so we limited a little bit at least. Okay? Now, if I were to graph this, okay, first of all, I need an independent variable. And what I'm going to do for my independent variable is I'm going to let x equal the day of the year. Okay? And I'm going to say it has January 1st, 2016 is x equals 1. Okay? Now that's important because this is not only good for January today is actually 402 days since January 1st. So we figured it out last period.
Oh, okay.
So we could, once we got our model, plug in 402 and see what it's going to be tonight, assuming our model is correct. All right? But using this and the data that we already have, on day 10, we are at 0. And on day 24, we are up at 100. Okay? And if I were to draw my sine curve, it would look something like that. All right? Now you'll notice I don't have a complete sine curve, do I?
No. Gotta make it up.
How much of a sine curve do I have?
Half.
I have half of a 1. All right, now let's think this through here. That half of a sine curve, if I were to draw the other half to come back down to 0, what day would that turn out to be?
Plus 38.
That would be day 38, plus another 14, right? So what did we just figure out?
28 days
Lunar
per
cycle.
cycle.
28 days per cycle, which is the period, okay? We just figured out that the period for our model is going to equal 28 days. Now, let's remind ourselves what our model is going to look like. Y equals A times the sine of bx minus c plus d. So at this point we actually can figure out one of the pieces in there.
B is equal to 28.
We can figure out b, but it's not 28.
It's 2 pi over b is equal to 28.
There we go. 2 pi over b is the period, so that equals 28. So if we solve for b, we are going to get b equal to pi over 14. Okay? So we're a quarter of the way done.
Oh, and D.
Okay?
Okay. Oh, wait, no.
So. Alright, so now we have one piece. We have b. Let's see what else we can get just from looking at this. What other things can we figure out here?
The horizontal translation.
Okay, what is the horizontal translation?
It's C over B equals 10.
You don't have c.
Horizontal translation is C over B, but that's not 10. Where is our sine
no,
curve going to
negative.
start?
Was
10.
at 0, right?
No, it's
Sine typically does start at 0, right?
starting at 10. It's shifted 10 units to the right.
It's not shifted 10 units to the right. The parent function looks like this, right?
Yes.
We could have used cosine. We chose to use sine, though. So remember, sine starts on the midline, right? Where is the midline?
For this one, 10 minus.
no.
No, it's 50, it's
100
50.
divided by
50.
50.
It's 50. It's 50. Good, okay? The midline here is 50. Which, by the way, that is what? It's our amplitude. It's also, in this case,
There's 2 points on that line.
it's the amplitude because we go up 50 and we go down 50 from the midline. So the amplitude, which is A, is 50. What else is that 50 though in this case?
The 50. Oh, is our vertical translation, right?
It's also the vertical translation.
Oh, yeah.
The midline was at 0.
Oh, yeah, 'cause it's
Now we've
50
shifted
on
it
the-
up 50 units. Okay?
Yeah, because it's supposed to be like 50 under and 50 over, right? Baseline.
Yeah, so look at this. We now know that our model is 50 times the sine of, we know b is pi over 14 x minus c. We haven't figured that out yet, but we know this whole thing has been shifted up 50 units. Okay? So just to kind of recap how we just got that, okay? Normally sine is centered at 0. Here sine is centered at 50, so we must have shifted the whole thing up 50 units. Also, from that 50, the amplitude is the distance from your midline up to the top or the midline down to the bottom. From our midline at 50, we got to go 50 down to get to 0 and 50 up to get to the top. Okay? Or remember, amplitude is just half the distance between the top and the bottom. So the distance here is 100%, so half of that's 50. Okay? So the last thing that we need here is that horizontal translation, though. And that probably is the most challenging part of this whole process. Okay? Let's look at our sine curve a little more closely at more than just one period. Okay? Notice that at the origin, what sine is doing. We always know that sine starts at the origin, typically for the parent function, but notice it's starting at the origin and it's on its way up, right? So in order to determine the horizontal shift, we need to identify a point where our model is crossing the midline on its way up.
1750.
What'd you say?
1750.
It's at 1750, exactly.
Because it's halfway between 10 and 24. Yeah.
We know because of the quadrants, remember the sine quadrants cuts it into quarters. We know that it's going to be exactly halfway between 10 and 24, despite what it looks like. And that's going to be at 17. Alright? So our horizontal shift is 17 days. Okay?
That's how you get it?
That's how we get it. So now, since the horizontal translation equals 17,
Alright, that's so much easier than C over B.
and we know, well, no, we still need C over B, because the shift equals C over B. B is pi over 14. Okay? So we have C over pi over 14 equals 17. We multiply by pi over 14.
17 pi over 14.
There we go. 17 pi over 14. And that's the last piece of our model. 17 pi over 14 goes right there.
Why?
Please. How do you get D and B over C? Okay. So, for D and B over C, D is always going to be where your midline ended up. Okay? Because our parent function had a midline at 0. So up here, it's evenly spaced about 50. Okay? So, here D is 0 on the parent function. Here D has to be 50. That's how far up we shifted it. Okay? Again, here the 17 comes from the fact that sine normally starts at the origin and is hitting that midline on its way up. So we look at our model here. Where are we hitting the midline on the way up? We're hitting the midline here and here. It's on the way up here.
Why does it have to be on the
Oh,
wall?
so C over B just is the sine is the middle.
Yeah, it's where sine is hitting the midline on the way up. Just look at what the x-coordinate is. That's your C over B. Okay.
Why wouldn't you pick the point 3150?
3150?
31
What's the
comma
other
50.
halfway?
Like why
Oh.
the other midpoint?
over here?
Yeah, like, would that give you a different answer?
Well, actually, you tell me. If I made my horizontal shift be 31, I could.
It'd be a cosine then.
No, it wouldn't be a cosine. It would be it'd still be a sine, but we would have to do
Flip.
what to it? We'd have to flip it across the x-axis, so it would be negative 50 sine.
Okay.
Which would be totally valid. That would be totally fine. Okay? That's the thing that sometimes is confusing to people, is like there's so many different answers. We used a positive sine model. You could have used this as your horizontal shift and made it a negative sine model. We could have made 24 the horizontal shift and used a cosine model. Or we could have made 10 the horizontal shift and used a negative cosine model. Okay? We could have done a lot with this. We could have, even if we really, really wanted to, gone backwards 7 days and found that at day 3 we were hitting the midline on the way down and made a negative sine model there. There's an infinite number of possibilities here, guys. Okay? So, here's the thing though. Everything else will be the same
Negative cosine.
except your horizontal shift and whether it might have to be reflected or not. But your amplitude, your period, and the vertical shift will remain the same, whether you use sine or cosine, and no matter how you horizontally shift it.
So, like, pretty much we should abide by the parent function in order to help us.
Yeah, definitely refer back to that parent function. Use that to help you, okay, and use these other identity things like the period is 2 pi over b, the horizontal translation is c over b. You got to know those things.
The equation for cosine is the same, right?
It is.
Cosine instead of sine?
It is, yes. Okay? Alright, so one other application here that I want to look at, and that is an application of trig to navigating. Alright, if you guys have been in physics, you've worked with this some already. Okay, but bearings, this is a very common way of measuring directions or giving directions. You know, you'll notice here we have highlighted, we have south 35 degrees east, north 80 degrees west, north 45 degrees east. Okay, I want to look at these a little more closely. That first direction, the north or the south, that tells us where we are going to start measuring our angle from. Now listen guys, the thing that can make this a little bit tricky is because we're so used to dealing with angles in standard position that dealing with angles given a little bit differently, you know, sometimes gets confusing. We kind of forget our context. Alright, but for this one we would start measuring from due south. Here we would start measuring from due north, and same thing with the third one. We would start measuring from due north. Okay, the second direction will always be east or west. And the east or west tells us which way we're going to rotate. Okay, so we're starting from due south. East is over here, so we're going to rotate that direction 35 degrees. Okay? On the top one, or on the middle one here, we're starting here at north. West is over this direction, so we're going to rotate 80 degrees towards west. Okay? And likewise, the last one, we start at due north. And we're rotating towards east 45 degrees. Okay? Now, one comment I will make is that if you are told that we are going northeast, that's this. Okay? anytime they just use the term northeast or southwest, they're talking exactly that direction, which is exactly halfway between north and east, or exactly halfway between south and west. Okay? So, we could just call this northeast, and we would automatically imply from that that it's at the 45.
Somebody said like north, south, or west, east. Would that be exactly where they were standing?
Then you would start to question their intelligence, I would think. So, yeah, north-south isn't a direction. So,
Yeah, it is. Stay with it.
alright. So, here's the thing. We can draw pictures using directions like this that will then help us in navigating or maybe figuring out where somebody is. Okay? This is how, you know, if there's a shipwreck or an airplane that goes down or something like that, they look at their directions, they look at their, you know, the vectors that they were flying along or whatever, and then they can use Trig and whatnot to help figure out where they probably were. Okay? If we draw this here, we have a ship leaving port at noon. Okay, so we're going to call this port. And it's going to head due west at 20 knots. Now, anytime they say due, they mean exactly west. So that's at a 90-degree angle from north. Okay? So here we're heading west at 20 knots, or 20 nautical miles per hour. That's what knots stands for. Okay? And it says at 2 p.m. we're changing course. So how far have we gone?
You've gone 40 miles.
40 miles.
40
Yeah.
nautical miles.
40 miles, 40 nautical miles. Okay? We're changing directions here. Now, anytime I'm drawing this and I change directions, I like to draw myself another little crosshair there so I can see my north, south, east, and west. That's just helpful. Okay? And it says that we changed course to north 54 degrees west. Well, here's north, and here's west. So I'm going to start at north and rotate 54 degrees towards the west. So that is my new direction. Okay? Now it says find the ship's bearing and distance from the port of departure at 3 p.m. So question, we've traveled for how much longer?
Well, another hour. So
Another hour. So how far did we go?
20 more
That
minutes.
way you went 20 nautical miles. But
We went
that way
20 more nautical miles. Now, what we are trying to find here
total.
is what is this distance, and also the bearing. We want to get this angle. We know it's going to be north something west, right?
Mm-hmm.
This make me feel
Well, you have to find.
So it's north something degrees west. Okay? Now, does anyone have any ideas about how we might go about solving this?
I kind of drew it out differently. I don't feel like it's completely wrong. I actually know it. Never mind.
Could you do two Pythagorean triangles right there?
I kind of, instead of turning, I kind of did two lines and did one that went with the 45 degree and one that extended that continued straight.
Can you do that?
And then that straight one went 20 nautical miles. And then I would do like a whole finding that missing angle. So I do 54 cosine
What?
times 20.
Okay, well hang on real quick here. You can't make the bottom side 20 nautical miles.
Aren't you going the same way? 20. Wouldn't that be the same thing?
No,
It's possible the units are.
because actually what Lorenzo mentioned is what we're going to use here. If I extend that and drop this straight down, I can look at this whole situation as two different right triangles, okay? But the 20 miles there is going to be what part of that right triangle?
The hypotenuse.
It's the hypotenuse,
Oh.
okay? It has to be the hypotenuse. Now, also notice the 54 degrees is not in our right triangle, is it? It is, what's the angle that's in the triangle there?
144 degrees.
90
Oh,
minus
46
54.
90 minus 54, so that would be
36.
36, okay?
Oh, I thought you meant in triangle with a hypotenuse.
Yeah, we know what you meant.
So that's 36 degrees. So the first thing that I would do is go ahead and figure out what the two sides of this little triangle are.
Top one is,
12 and 15.
Hang on, what?
Like a square plus b square equals c square. That's not easy.
Well, here's the thing with that. We can't find d using a squared plus b squared equals c squared because
Not right.
that's not a right triangle.
Do we have a calculator when we're doing this?
Oh yeah.
It's like
Oh, yeah.
plus 54 plus 90, then we can use like the sine, cosine, because we know like the length of the two sides.
Okay. If we had learned it yet, we could use something called the law of cosines. If you've seen that before and you know what that is, then you'll realize that that's a whole lot easier, okay?
Yeah, that's a
We
formula.
just don't have that tool yet, at least not officially in our class.
I got it. I got
Okay.
it. I got it, but I forgot it. It's like a really long formula that gives you like all the angles and all of
Yeah, you can use that to
For
figure
any
all that
triangle.
stuff out.
Can't you just find like cosine of 36?
Why would you use the
then
tangent? It almost
multiply 20 by that?
Okay,
Because it only works for like.
let's look at this. We are gonna do that. We have a right triangle here on the left.
I just.
So let's,
54 and 36.
you, like Grant said, let's use the cosine of 36, and that is gonna be x over 20. So we multiply by 20 and we get that length of the side to be what? Use your calculator. In degrees.
Oh, I already found 16.1.
16.1,
16.18, I'm sorry.
okay, alright. So 16.18 miles.
I don't know why it's 16.18, I'm sorry. X is,
Oh,
Grant, failing us already.
yeah, I'm already ruining everything. It's kind of what I do.
alright. So wait, you did, what did you use to find y?
Everything is good, Harold.
Sine.
Wait.
Should be sine, right?
Sine 36.
It's y over 20. So you got y equal to 16.18? Is anyone verifying this for us?
One of them is 16.18. I can't figure out what I did.
Come on guys, all of you have calculators, get them out and do it, okay? You've got to be able to do this on your own. You can't sit there and wait for someone else to plug it
It has to be
in.
in degrees, the calculator, right?
Yes, make sure your
Okay,
calculator's
that's-
in degrees.
Yeah, I got 16.18
Yeah,
For y.
for x.
I'm sorry, X is 11.7.
No, x is
No,
16.18.
no, for X, for Y I got 11.76.
Wait, no.
Yeah, x is 16.
Hang on, stop. Which of these has to be bigger?
X does.
Why?
Because the angle in the top right, top angle is a little bigger than 36.
Yes, this is 54, that's 36. X has to be bigger, alright? So if you get confused as to which is which, double check. Alright? So, who used cosine to get x? And what'd you get?
16.18.
16.18. Alright, thank you. 16.18 miles.
Right, killing us.
Now, who got y?
I think it's 11.76.
11.76?
Yeah, he's right.
Yeah. That,
Okay,
I think.
but
so that's 11.76.
For some reason it seems somehow.
Now, check out what we've got here. We now have, if we kind of take out the middle part,
Yeah.
we have 11.76 and we have 56.18. Okay? Here's P. Here's the distance we're looking for. Notice I just added the 40 and the 16.18. Okay? So now we can use the Pythagorean theorem, a squared plus b squared equals d squared in this case. Alright? And also, we're going to need to figure out this angle over here, okay?
Well, wait, I got it.
What?
For that angle, since like adjacent, whatever that adjacent property thing is, since your inside is 36, doesn't that top left, oh,
We don't know that's 36. We got to figure that out. So let's do theta here, and we'd have tangent of theta equals 11.76 over 56.18. In this part, we haven't quite gotten to yet. You have to hit inverse tangent,
Inverse tangent of that.
okay?
Wait, what?
So you have to hit second tangent of 11.76 over 56.18. And what did we get for an angle there? Alright, so we get 11.8 degrees. We use the Pythagorean theorem to get the other thing, but notice that's not the bearing. The bearing would be this up here.
yeah,
It would be 88.2 degrees. So coming back here, it's north 88.2 degrees west. And then whatever that distance we get off the Pythagorean theorem. Okay?
squared plus,
Yeah, for the distance we would use 11.76 squared plus 56.18 squared equals the distance squared. So you square root it and you get 57.40
And that's the answer.
miles. So that's how far away they ended up. And the bearing to get there would be the 88.2, north 88.2 degrees west.